James, are we on? Okay, this is the last class of the semester, or at least the last class in this course this semester. I'm going to go partially through an example, which is a harder version of one of the homework problems due next week, which you are going to do, but not hand in. I would like to leave some time today for you to ask questions about just logistics about the end of the course. So if I forget somehow and it gets to be 5 minutes to 11, stop me and we'll do questions and answers about just course logistics things. Okay. So I don't know if it's appropriate to talk about things like this in class, but anything, there's a dynamics way of looking at things, and I don't know who was paying attention to the news and the big events earlier this week, but finally we, and I don't know if you include yourselves as part of this, we tried to do something that we've tried to do for years, and a big thing, and we finally got it accomplished, and there's a dynamics way of looking at that thing. So I'd like to show you that. And it goes like this. For years, we've been trying to get a robot to walk 26 miles. and finally, this past weekend, we succeeded in getting a robot to walk 26 miles. And this was the big news earlier in the week that was drowning out all the other news, at least in my mind. So here is a video of that robot. This video is a few years old, but it shows how this thing works. So this is back when the world record was 1 kilometer, but we've took this video and added some music. I'll show it to you. The main thing you want to look at here is this robot is a little stupider than the one I showed you before, in that it doesn't have knees, and it's got 4 legs instead of 2. We call it a 4-legged biped, which is a joke that nobody gets. They look at me sort of quizzically, and they don't know what I'm talking about. But you're supposed to laugh when I say 4-legged biped. Anyway, it's the 4 legs are to keep it from falling over sideways. It's a kind of stupid robot, but this is the one that we are using to try to understand the control. What's nice about it for this class today is that it's a double pendulum. It's 2 sticks. They're not, one of them's hanging up and one of them's hanging down, but it's still a double pendulum. And then the question is, how does this thing work? And here's some audio that explains how it works. Now this is Laurie Anderson again. Why is this so funny?
It's a great video.
What?
You're walking, and you don't always realize it, but you're always falling. With each step, you fall forward slightly, and then catch yourself from falling. Over and over, you're falling, and then catching yourself from falling. And this is how you can be walking and falling at the same time.
Okay, now you hear the big crowd. We can't see the big crowd, but there's a big crowd there watching this. There's 4 of us in Barton Hall at 2:30 in the morning. Now this week earlier there was about 10 or 15 of us all night long on Sunday night. And the robot walked, we wanted it to walk a marathon, and it walked 40 miles instead of 26. So the previous record was 14 miles, and the previous record before that was 12.8 which was held by the Big Dog robot of Boston Dynamics. Big Dog is a more famous robot. Who knows the Big Dog robot? Big Dog you probably know it because it's the one that on YouTube goes, and there's 6 different parodies of it on YouTube. Okay, anyway, that one walked 12.8. Ours walked 14.3 last summer and 40 miles on Monday.
And you completely blew the old record out of the water.
That's what we think, yes. So maybe in secret. So the last time we broke the record, then the Boston Dynamics people sent me an email, so, well, oops, we just went. I mean, we had 5 miles, and they said, well, we just went 12.8 miles. And then we said, well, we went 14.3 miles. And now to stay out of their reach, we just went 40 miles. But who knows? They'll put a bigger gas tank on Big Dog, and they'll go 50 miles. Yeah, so it makes the turns. It's got the middle legs twist. So when the middle legs are on the ground, they twist, and the robot goes like this. It knows what's to turn because there's a remote control for turning. So it's autonomous. It's autonomous in terms of the walking control, but the steering is done by a person. Yes?
So just to figure out, how long did it take to cover 40 miles?
It took 30 hours, 49 minutes, and 2 seconds.
I'm assuming you took turns watching?
We took turns steering and watching. Undergraduates were involved, too. We all got tired. Okay, so you see a double pendulum there. So I wanted to talk about a double pendulum, and here's a demo of a double pendulum. It looks like a double pendulum because there's 2 pendulums. This is not usually what people mean by a double pendulum, 2 copies of one pendulum. But let me just show you 2 copies of one pendulum. So here's a pendulum, and it obeys equations, which you should know how to derive the equations of motion about 5 different ways by now. And here's another pendulum, and all of those derivations work. You can just photocopy them. They work for this pendulum too. And we believe we live in a deterministic world. And not only is it a deterministic world, but it's determined by the laws of mechanics. So when you take 2 different things and give them the same initial condition, we predict the future with our crystal ball. Well, it could be our crystal ball in MATLAB, or it could be actual reality itself, and you do the same thing, and you get the same result. Now, if we let this go for a long time, they'll drift out of phase. How many cycles does it take for them to come around?
I kept missing when they came back.
What?
160.
160 cycles. So after 320 cycles, so this is accurate to 1 part in 320, and that's a machining error. They're meant to be identical. Okay.
It also depends, isn't it nonlinear at first?
Well, if the equations are always nonlinear equations, it's the basic equation is theta double dot is equal to minus something times sine of theta. And that something has to do with g and mass and moment of inertia and so on. But sine of theta is well approximated by theta itself. So if you just write the harmonic oscillator equations with the right coefficient, you get very nearly the right answer down here and very nearly the wrong answer up here. Here's where we can see, remember I said, how does the period change with amplitude? Here you can see the period gets quite long when the amplitude is very high. 1, 2, 3, 4. That's longer than here. 1, 2, 3, 4. And then the period goes to infinity when the amplitude gets to pi. Okay, so it's nonlinear equations. Here, how accurate are the linear equations? Depends for what purposes. If you want to know just the period and things like that, they're quite accurate up to 45, 50 degrees. Even 90 degrees is not so bad for the period. We can see that. We can do the experiment right here. Oh, it's not that great, but let's try 45 degrees. Pretty close. But now down here, it's supposed to be the period is independent of amplitude. And that's pretty good. Different amplitudes, same period. So that's the harmonic oscillator equation where you have the linear equations, and if you multiply by a constant, you still get a solution, which means the period is independent of the amplitude. So for small, and it's because the period is independent of amplitude that they based clocks on pendula. And if you look at the accurate clocks, they have very small amplitudes because they don't want this nonlinear variation. Okay, so that's what a double pendulum is not. We don't mean by double pendulum 2 pendulums side by side. we mean by a double pendulum, something that has 2 degrees of freedom, like this. And this then is that walking robot, very nearly. If you leave the ankles out, here's the ground, here's the one leg, both the thigh and the calf, and here's the other leg, the thigh and the calf, and here's the body up here. And that walking machine is very nearly obeying the double pendulum equations in this regime. Okay, so that's why double pendulum is interesting in our lab. Now, there are interesting things about a double pendulum in that down here we have linear equations, and what kind of motions do we get? They're motions that are all reminiscent of what you got when you had 2 masses on the air table. You could find there's nice normal mode vibration, which I can almost get like that. That's one of the normal modes. And another one is like this. If I didn't quite get it right. And these are things you can find with eigenvalues and eigenvectors, just like the way you could find with the 2 masses. So if we wrote these differential equations, which is the main content of today's lecture, and linearized them, we would have equations that look like, structurally like the 2 masses on springs from the air track, and we could find these normal mode solutions. And even things which look complicated for small motions like this, we can think of as a sum of 2 sine waves with different frequencies. And if you add 2 sine waves, different frequencies, they beat in complicated ways. The thing about the double pendulum is that it's essentially more complicated than that. So already if you had 2 sine waves with 2 different frequencies, it looks complicated. But double pendulum is the most famous example of this phenomenon, which is that it looks kind of innocent, but it does crazy things. So it's sort of one of the simplest mechanical examples of what's called chaos, which is you write these deterministic equations down, and they do funny things when you run them in time. And now could this possibly be like a sum of 2 sine waves at 2 different frequencies? And it's not. So you can if you set up the differential equations, which you can do in the homework, run them in MATLAB, you will get these funny solutions. One feature of these funny solutions, which is different from the small amplitude motion. So the small amplitude motion, if we start it, let's find a sort of complicated one. That's sort of complicated. If we take 2 different things and start them the same way, they do the same complicated thing. Now, after a while, they'll drift apart because they're not exactly the same, but they do basically the same thing. On the other hand, in this nonlinear regime, in this chaotic regime, we give initial conditions the same, and they very quickly diverge into different motions. And that's one of the features of chaotic systems, is that very small differences deviate exponentially in time. And that's why they have this so-called butterfly effect, which is if you think of the weather system as being a big nonlinear differential equation, that some butterfly wings flap in South America causes a hurricane in the Caribbean, because the whole weather system, just teeny differences grow exponentially in time. And in some way that is true, the butterfly effect. You don't know which butterfly wing where did it, but if you just take the dynamical system of the Earth or the Earth's atmosphere, run it in time if you knew all the differential equations perfectly accurately, and then run it in time again with a slightly different initial condition, the butterfly wings flap, you will get differences which are analogous to these differences here, which is why weather forecasts are no good when you go ahead in time, 6, 7, 10, 12 days. Okay, so this chaotic aspect of double pendulums is not what we use for the robots. The robots have this chaos, and some people are interested in it, but I'm not. In fact, a friend of mine at meetings, whenever somebody gives a talk about chaos and walking, that the walking differential equations have chaotic solutions, he leans over and says, and mutters in my ear, he says, "It's all your fault, curse you, because we wrote a paper about chaos and walking, and I think it's stupid, but it's somehow magnetic. This chaos thing is magnetically attractive to people." Okay, any questions about the double pendulum, about the walking mechanics and so on, before I get into how do you actually write these differential equations? Okay, the video, I'm going to put away the projector. So the video, except I wanted to show you one more thing on the projector. Which is, I found that you guys hate it when I go through MATLAB code, so I'm just not going to go through this code. But somewhere here is a MATLAB, and you can set up this simulation and get this double pendulum here. So what I want to show you today is sort of the mechanics, as in F equals ma, that it takes to write the differential equations that you can plug into MATLAB to get this thing to go.
Damping in that?
In the simulation, I think I did not put any damping in. Did not. So this one will go and go and go. And it will slowly build up or lose energy because of numerical error, not because of damping, but very slowly. Because I'm using a better integration method than that first one we did in the semester, the Euler method, which sinks and builds up energy. Does that address your question? Any other questions? Okay, then the computer is going to go away. Off. Okay. So we'd like to be able to write the differential equations for a system like this. Before we draw free body diagrams, you want a neat sketch. Too many of you are drawing sketches in general which are too small. I'll just repeat one of my pet expressions is don't crowd your confusion into a small drawing. If you want to make something clear, make it big. And if you don't understand it, then make it really big and not understandable so you can confront your misunderstanding rather than have it blur into a little picture where you say, I don't quite understand it, and the picture's really small, so you somehow give yourself an excuse for not thinking it through. Make it big and clear, and then confront it. So I would recommend that in general, for this course and other courses, kill trees. Okay, so we're going to keep track of this thing. How many degrees of freedom does this? Let's just do one double pendulum. I'm not going to call this a quadruple pendulum because it's two double pendulums. Let's just look at 1/2. How many degrees of freedom does this have? 2. And why do you say 2? Well, it's got an x and a y coordinate and a theta for this object, and an x and a y coordinate and a theta for this object. So in terms of dynamics, there are 6 configuration variables we can pay attention to. And on top of that, there are 6 velocity variables we can pay attention to. The velocity of the center of mass, x and y components of both of them, that's 4, and 2 angular velocities. So there are 12 numbers we might want to pay attention to. But if we knew this angle, the angle of this object, and the angle of this object, and we knew the rate of change of those 2 angles, we could figure out all of the velocities and accelerations of all of the atoms in this in terms of their positions. Okay, so we say it has 2 degrees of freedom, and then it takes 2 numbers to describe the configuration. Okay, so what numbers do you want to use? We could use the x-coordinate of this one and the x-coordinate of that one. What's bad about that as a choice of numbers is that when this is in this position, it's got the same x. So 2 different positions have the same x. So long as we're only looking for motions down here, we could use x1 and x2 as the degrees of freedom, or maybe even y1 and y2, but they're just not very natural coordinates for this thing, which obviously has to do with circles somehow. And the most natural coordinates are these angles, theta 1. And now, what do we use for the second angle? There's no right or wrong answer to this. Some people like to use this angle that goes from the extension out like this. If we use that angle, then when we write the differential equations, we are naturally going to be led into using the various formulas that you've just been learning recently about relative motion. It turns out that it's a little easier to put the differential equations together if you use the absolute angle instead of this relative angle. That makes the equation simpler. It makes them a little harder to interpret, especially in the world of robotics, because on a robot, when you go to measure this angle or control it or power it, the angle which you're powering is the relative angle. So this is what you see on a video camera, but it's not very intrinsic to the machine. Or if you're interested in friction, the friction has to do with the sliding, which is associated with the relative angle. But to keep this lecture simpler, I'm going to use this absolute angle. Then we have to pay attention to the geometry of this thing. And so we have some length here, L1. This thing has some center of mass, called as G1. So we have to pay attention to this distance here. I'll call that R1. This thing has some point G2, and we're going to have to pay attention to that distance, R2. This total length actually isn't going to show up in the differential equations. This thing has some mass M1, and it has some moment of inertia about the center of mass. I could call it IG1, or IG, there are different ways I could label that. And this one has some M2 and IG2. Now we've got to use x and y coordinates just so that the polar coordinate formulas are simpler. With these angles, it's nice to use x and y coordinates like this so we don't have to rederive all the different polar coordinate formulas. Now what's our goal? Our goal is to be able to do this MATLAB simulation. We'd like to know how this thing moves. We might actually want to know the forces in the joints, and we could figure those out afterwards using other equations. But to start out with, we want the equations of motion. What's a way of thinking about what are the equations of motion? What we say is, given all of the geometry and mass parameters, and also given theta 1 dot and theta 1 and theta 2 dot and theta 2, find, and now think to yourself what I'm going to write next. 5 seconds to think about it. What we want to find is we want to predict the future, which means we want to predict the future of these things. We can predict the future of theta 1 if we know theta 1 dot. We can predict the future of theta 2 if we know theta 2 dot. But if we want to know the future of theta 1 dot or theta 2 dot, we need to know theta 1 double dot and theta 2 double dot. So our goal is to write theta 1 dot is equal to, and I can call this thing omega 1, and we can also write theta 2 dot is equal to omega 2. So we think of those things as given in time, but then we want to supplement these with omega 1 dot is equal to question mark, and omega 2 dot is equal to question mark. And this is what we would call the equations of motion, is these right-hand sides of these two terms here. So that's our big project, is filling in those right-hand sides. Okay, in terms of what we're trying to do in the organization of work, do you have questions about this setup? Somebody ask a question. What question do you wish somebody else would ask? Yes?
So we're keeping track of the angle that the second angle makes to the angle back to the first one?
Is it worth keeping track of that? It might be that some expressions may or may not be simplified by looking at that angle theta 2 minus theta 1, and it might be not. The way it actually works out is that if you start out, so let's say defining this angle as phi and write the equations in terms of this, it works more the other way around, that the nicer angles are theta 1 and theta 2, in my experience. Now, who did you wish would ask that question? Okay. Another question? Okay, so how do you go about doing this? Is you draw free body diagrams. And how many free body diagrams are there we can draw? Well, there are 3 natural free body diagrams. Object 1, object 2, and the set of them together. Let's call object 1 script A. Let's call object 2 script B. So immediately becomes confusing because of script capital letters. How many people can write the whole alphabet in script capital? Some not, right? In cursive, right. It's just as bad as Greek, right? Even though you learned it in 3rd grade. Most of us forgot it. Okay. What? Even though you learned script capital letters in 3rd grade, most of us still don't know script capital letters now, except for the first letters of your first and last and middle names. Okay, so we have free body diagrams. What can we draw them of? We can draw them of A. We can draw them of B. And we can draw them of A and B, which is what we call the system. And A looks like this, B looks like this, the system looks like this. And now what goes on these free body diagrams? The simplest one to draw is this one. We have M1G down like this, and then we have reaction forces. And just to keep the signs consistent with what's over there, we have these two reaction forces. And we're going to go to some trouble to not have these forces show up in the equations of motion. Why not? It's because everything is confusing enough with so many variables around that we might as well try to do things, organize things in a way so that we only have to write 2 linear or angular momentum equations and not, how many are there that we could write sensibly? For this problem, how many sensible and independent linear and angular momentum balance equations could we write? Think about it for 30 seconds. Actually talk to your friends. Actually, let's make this the quiz question for the day. Talk to your friends. Please talk to your friends about mechanics. Any questions about the question? Questions about the question? How many independent is the key word here, linear and angular momentum balance equations can we write for the system? You can write an infinite number of them, but if you write an infinite number, most of them you could get to those equations by linear combinations of the other equations. Okay, 30 seconds more. Okay, 5, 4, 3, 2, 1. Lock up the vote. Now I'll show you how you voted. That is A, B, well, so almost symmetric, so you don't have to know which one, but it's A, B, C, D, E. Okay, so the majority here voted C. Now what is C, and how did I distract you with that? We have only two independent free body diagrams, because the system free body diagram comes from the other two. For each of these objects, we can write linear momentum balance and angular momentum balance. Linear momentum balance is two equations for a two-dimensional problem, x and y components. Angular momentum balance is one. So we have 3 plus 3 is equal to 6. So the right answer here is E.
It depends on if you use vector notation.
It depends on whether you use vector notation. So let's when I say independent equations, I'm talking in linear algebra language, and I mean independent scalar equations always. Okay, so one linear momentum vector equation is, we can't talk about two vector equations being independent because each of them is already two equations. Okay, any questions about this question? Right answer is 6, which is none of the above. Questions about it or doubts about it? Okay, so we have this free body diagram. Now, what happens at this free body diagram? Sorry. We also have here reaction forces on this object. And if I pick these like this, I'm going to have to label this point. Let me label this point C to keep it, even though we've got script and other letters, just keep it C so there's not a possibility of that confusion. So we have this point C, and we have this point O. If I have these two forces here, I have to have two forces here like so, by action and reaction. So I can't actually make a nice sign convention here. So I could call this thing Cx and this thing Cy, and this same scalar Cy has to multiply by an opposite vector acting on this one, and this same scalar has to operate with an opposite vector here. So any questions about this part of this free body diagram? Now the reason I've labeled them is, even though I'm going to try and get rid of them in the equations of motion, is just so you see how they look on the free body diagram. Then what else do we have here? Is we have here M2G. Now in this free body diagram, we have these same two forces. Let me call this ROY and ROX, just to show that these two are exactly the same two. And this is not redundant, because it's actually the same forces. What else do we have? We have this M1G, and we have over here M2G. What about this force here? We don't show it because it's an internal force in this system. Any questions or mistakes about this free body diagram? Questions about the free body diagram or mistakes that I made? Yes?
Do you have the y, like the y and CX, CY shouldn't be CY, CX?
Shouldn't I call this CX? I can call them whatever I want, but it would be more natural to call these CX and CY and CY and CX. Any other questions or mistakes? Okay, so now we would like, of those 6 independent equations, those infinite number of equations we can write, towards the end of getting these most simply, we'd like to write 2 equations which don't have things we don't know about and don't care about. And I'm not going to make the usual joke because it's too untimely now. But we want to not have in the things we don't know about and don't care about. So what are equations that we could use towards that end? Which free body diagram in which of the equations of motion? Any volunteers? This is your big chance. All semester, you haven't asked a question. Okay, I'm going to promise not to pick on you. Who thinks they know? Just raise your hand, and I promise not to pick on you. Are you willing to be picked on?
Sure.
Okay, yes?
You do for B around C angular momentum balance, and then for A and B you around the center right there.
Right, so for this system, if I use angular momentum balance about this point, then that equation of motion does not have these forces which we don't know about and don't care about. And it has in it these things which we do know about and do care about. If for this system we use angular momentum balance about this point, it has in it the things we care about and doesn't have in it the things we don't care about. Then we will have two equations which have in them these two unknowns, and also have in them all these things which we think of as knowns. So we could then take those equations and using linear algebra, not differential equations, we could solve for these two unknowns. So the method is we're going to use angular momentum balance about this point for this system and angular momentum balance about this point for this system. Okay, so we're going to take angular momentum balance about point O for the system, and we're going to take angular momentum balance about point C for body B, and these will be two equations which we can solve for omega 1 dot and omega 2 dot in terms of the so-called known quantities. And we think for these purposes of the angle and the angular rate as being known quantities because as we solve the differential equation in time, we will know those at any instant in time. Now what happens is these equations are pretty complicated, so the algebra is tedious, and I'm not going to get through the algebra, but the method is all stuff which you can understand. So let me just, since I don't have time to write out the full equations, let me pick just one of those. So let's just start with angular momentum balance for the system about point C. Okay, so that was angular momentum balance for system about point O and angular momentum balance of B about point C. So how does this work? We say the sum of moments relative to point O is equal to rate of change of angular momentum relative to point O. Now the left-hand side is all stuff from statics. So what goes in the left-hand side is the position of G1 with respect to O crossed with M1G in the I direction, plus the position of G2 with respect to O crossed with M2G in the I direction. And now we're going to set this equal to this H dot stuff on the right-hand side. Now for this to all make sense, we have to be able to evaluate every term in here in terms of the stuff that we think of as given, the top part over here. So what does that mean is we have to look, for example, at R of G1 with respect to O, and we say, what is that? That's R1 cosine theta I plus R1 sine theta j, and that's a theta 1. So we've written that thing in terms of all known quantities, or the quantities we think of as known. Go ahead, please ask out loud. What? But you have a comment. Would you like to share something with the class? Okay. And similarly, we're going to have to write RG2 with respect to O, all in terms of things that we think of as known. And what is that? That's L1 times exactly the same quantity, theta 1I plus sine theta 1 I plus R, what did I call that? R2, even though there is, well, there's an R1, plus R2 cosine theta 2I plus sine theta 2J. So if we're going to write this giant equation all in terms of theta 1s and theta 2s, we have to be able to write the things which we think of as simple here in terms of those theta 1s and theta 2s. So you can see how this blows up into a giant expression just immediately. And the right-hand side, which I haven't done yet, is going to blow up even worse. Now for the right-hand side, we have two parts. The angular momentum, or rate of change of angular momentum, is the sums of the things having to do with the motion of the two different collections of atoms. So we have two rigid objects, and we look at the rate of change of angular momentum of each of the objects and add them up. So for the first object, we have the position of G1 with respect to O, crossed with the mass of 1 times the acceleration of object 1, which we call A, which we called G1. And we have plus I G1 omega 1 dot K. And then we have the same concept here, RG2 with respect to O crossed with M2 AG2 plus I2G omega 2 dot K. Now we have to fill in all of these things in terms of known and unknown quantities. Here we have the objects of our desire, the things we're trying to find. So we're going to take this equation and the other equation, which I didn't write down, and solve for this omega 1 dot and omega 2 dot in terms of things we know, but we have to fill in the things we know. These two we've already got, because I just did them on the board over there. But how about the acceleration of G1 and the acceleration of G2? So, the acceleration of G1, the simplest way to write that is with polar coordinates. And so the acceleration of G1 is minus omega 1 squared, the position of G1 with respect to O, plus omega 1 dot K cross the position of G1 with respect to O. Now what about the acceleration of G2? This is probably the hardest term in the whole giant equation. And we're going to need this again when we write angular momentum balance for this second object about C. What is this one? Well, it's the acceleration of point C plus the acceleration of G2 with respect to C. So now we need to fill in these two quantities. The acceleration of point C is minus omega 1 squared, the position of C with respect to O, plus omega 1 dot K cross the position of C with respect to O. What's the acceleration of G2 with respect to C is the position of G2 with respect to C with a minus omega 2 squared plus omega 2 dot K cross the position of G2 with respect to C. So that means we're going to have to fill in what is the position of G2 with respect to C, what is the position of G1 with respect to O, and these are things which you can fill in easily enough. They look just like the expressions above with different lengths in them. That means that we know all of these expressions in terms of theta 1 dot, theta 2, and theta 2 dot, which means that we get from this, if we want, one equation that has in it two unknowns. This is one equation with two unknowns. And the two unknowns in this are omega 1 dot and omega 2 dot. Then if we take angular momentum balance of the same system about C of this object B, That will also give us two equations for these two unknowns, which means we can solve for omega 1 dot and omega 2 dot. Lots and lots of algebra, and this implies that we can write ODEs for MATLAB. Now, how much algebra is it? I would say, if you want to get it right, you should give yourself at least 4 hours to do this problem. At least. And probably you're better off using symbolic calculations with Maple or the symbolic toolbox of MATLAB or Mathematica or Maxima or something like that. Okay, any questions about this? So it's all set up in principle how to substitute all this in, but once you substitute this all in and do all these cross products, we have a giant expression here, and then we're going to get another giant expression, and then we have to do the algebra to sort out, to solve those two simultaneous equations. So they turn out to be linear equations for omega 1 dot and omega 2 dot. Okay, now, questions about absolutely anything related to this course. Or if you like, questions about absolutely anything.
Python?
I do not happen to like Monty Python, but I like John Cleese. And he has a skit, which you can find on YouTube, called Funny Walks, or the Ministry of Funny Walks, and I happen to like that skit because it relates to a paper I wrote a few years ago. Wait a few minutes. Yes?
What powers the robot?
Say again, what powers the robot? That particular robot has 4 motors. One which powers the outer ankles, one which powers the inner ankles, one which swings the legs, and a 4th small motor that twists the inner legs for the steering. And the power comes from 7 lithium-ion batteries, each of which are nominally 25.9 volts and have an 450 watt-hours of power, of energy. Yes?
How much of that improvement is due to the improvement in the battery versus...
The improvement from last summer, where we had 14 miles, versus this time when we had 40 miles. The efficiency measure for transportation is called the cost of transport, which is the energy per distance per weight, or the power per velocity per weight. And last summer that quantity was 0.49. And this week we got it down to 0.28. So we reduced it by about 40%, 45%. Human beings have a cost of transport of about 0.2, so our robot still is not as good as a human being. We think we can get it there, but we decided to go for this record attempt because the batteries were good enough anyway. Yes?
You could eventually make a mail carrier out of it?
Let me answer that a different way. Most of the people who are in robotics have this fantasy about robots being useful and serving society and serving coffee and killing people and things like that. And I do not have that fantasy. I think walking robots are useless, and that's not what it's not that I think they will help deliver the mail that motivates me. Does that address your question? Yes, in the back, Neil?
Well, like, what I'm thinking, I'm just trying to think how, because like...
You're trying to think how what? I missed the word there.
Like confiscate.
What?
Like a confiscate, when you walk. Well.
Yes.
So like, what I was thinking is in reality when I walk, I kind of lean this way, when I pick my foot up and I lean the other way.
Yes.
So, so I was kind of wondering if it's really possible to recreate that at all, or...
So the robot that I showed you was a 3-dimensional object, because all objects in this world are 3-dimensional, but it was doing something which we think of as 2-dimensional. We do have robots which are genuinely 3-dimensional, and we want to build more of them. They're just harder to analyze and harder to control. So if you look at the videos on my webpage, you will see we have robots which wobble from side to side, even more than people do, and looks like a penguin or something like that. And yes, it's possible to replicate that, and the equations of motion in 3 dimensions include that. But since you brought that up, let me just point out, here is a relatively simple problem in 2 dimensions, which is this double pendulum, and already the equations get horrendously complicated. If I had a triple pendulum and I gave it to this whole class and I said, everybody work in pairs, you have nothing else to do but write the equations of a triple pendulum, come back to me in 2 weeks. You have 80 hours to work in pairs, 160 hours per pair, and each of you come back. I would have high confidence that none of you would have the right equations. Not because you can't do it in principle, but because there's so much algebra, you would all have algebra mistakes. When you go to 3 dimensions, the equations become complicated in ways which we have not really discussed in this class, because in this class we have moment of inertia as a scalar. In 3 dimensions, this quantity about distribution of mass is a tensor, a matrix. And then we pay attention to rotations, whereas in this class rotation is an angle. In 3 dimensions, you cannot help but think of rotation as a 3 by 3 matrix. So when you go to write, say, analyze a robot with a 3-dimensional model, even if you think of the robot as just a double pendulum, but a 3-dimensional double pendulum, the analysis becomes much, much more difficult. Okay, so my PhD student who basically did a double pendulum model of 3-dimensional walking, it took him a few years to get equations that he trusted, just for a double pendulum. Okay, does that address your question? Okay, how about logistics questions, final exam, studying? Do we have to? I think I've told this story before, but I visited my sister when she was in college and I was applying for be a college professor. This professor gave this lecture, which I could tell he was really excited about, like I'm excited about my robots. And at the end of the class, he asked the class, are there any questions? You know, just expecting them to ask interesting questions like you're asking about the robots. And the only question he got was, do we have to know this for the final exam? And I thought, that's the job I'm applying for. Okay, so, and you guys have done very well here. You've asked only about the robot. But do you have any questions about the final exam? Yes?
Are you going to teach any more of our classes?
Are you a sophomore?
Yes.
I'm going to be gone all next year, so perhaps when you're a senior, you can see what I'm teaching. And avoid it, probably, is what the other people are thinking. Yes?
What upper level classes do you teach?
I often teach the next class in this sequence, which is called TAM 5700. It's a first-year graduate class, but basically the only prerequisite for it is this course. So I may or may not be teaching that in the fall of 2012. I don't know. Where am I going? I'm going to Finland. I'm going to an island in the Baltic Sea, which is actually closer to Stockholm than to Helsinki. It's closer to mainland Sweden than Finland. It's a Swedish-speaking island, and my wife studies insects there, and I'm just basically following her and doing for work what I usually do, which is email. Yes?
Is there something particular that we should look for on the website that you're expecting?
Is there anything you should look for on the website? Yes. In particular, office hours next week are on the website. In particular, there's advice about how to study for the exam on the website. Okay, goodbye. Good luck to you.